Good morning, good afternoon, or good evening, depending where you guys are or what everyone is. Today, I'm going to talk about managing scale and complexity from the event-driven approach perspective. My name is Harrington Joseph. I'm a senior software engineer at Netflix, where I'm part of the data platform orchestration team. My work is focused on architecting and developing the next generation of scheduling and orchestration tools, as well as the event-driven platform, given that they are highly related. Let's use a simple analogy to set some context for this talk. So imagine a world where there are no alarm clocks, but in which you still have to wake up on time. How would this work? Would you still be able to get a good rest? It is very likely that you're either going to wake up multiple times in the middle of the night to check the time, or that you're going to end up waking up late. In the real world, we rely on simple events such as an alarm clock going off in order to wake up on time. Without this very simple event, we would have to deal with inefficiencies such as waking up multiple times, poor sleep quality, or sleeping longer than we're supposed to. As living beings, we perceive events around us and we react to those that we care about. But when it comes to software architecture, we tend to design systems in a similar way to that imaginary world that I described at the beginning of the analogy, leading to a high waste of resources and scalability issues. So expectations. This talk is focused on architecture design, making a special emphasis on microservices. However, same concepts and techniques can be applied to other designs. So the problem, scalability and complexity issues that come from natural and organic evolution of coupled services. What does this mean? It means that as systems evolve, very naive and simplistic approaches get developed, leading to coupled services. As a result, this natural evolution creates rigid, complex, expensive, and in some cases, impossible to scale systems. So let's talk about natural and organic evolution of a system. Say we have a system where movies are registered. Let's call this the movie register service. So every time a new movie shows up, we basically go and post a new title to the movie register service. Very simple, right? Soon enough, the company evolves and you find yourself trying to gather more information about the movie that got posted, for example, the actors, producers, directors, studios, etc. The initial approach might be to gather all this information in the movie register service. But as things evolve, maybe a different team is probably going to take the responsibility of developing a more robust service to gather all this metadata. So the metadata service is born. This usually leads to two very common approaches. One, the metadata service is going to constantly be pulling from the movie register service, trying to find out if there is a new movie. Two, the registry service is going to engage in some kind of contract and notify in a synchronous way the metadata service about a new movie that has been added. Either way, this means direct and constant communication between these two services, which cause performance issues for both in the long term. Now, say we have another service, and this service is there just for search purposes. So this service is going to index movies, movie titles, and movie metadata to make it available for search purposes. So in this case, very likely the search indexer service is probably going to have to be constantly pulling from these two services in order to find out if there is new data to be indexed. Now, a recommendation system shows up and it's on the same boat as the other ones. It's constantly pulling information from the metadata service, from the movie register service in order to crunch some recommendation. And it's probably going to also write or communicate with the search indexer service to post the recommendations for search purposes as well. Now, reporting. We have a reporting service. The reporting service may need to execute some reports on the periodic basis, meaning on the daily basis or hourly basis or something like that. But it may also need to execute a report when something happens. Say when a movie shows up. So that means that it's constantly pulling from the movie register service or any of the other services. So you can see where this is going. As the system provides new functionalities, new services are starting to show up, and more requests and connections are made between them. And this definitely works, don't get me wrong. But as things evolve, this direct coupling makes the whole ecosystem very rigid and hard to scale. So the natural and organic evolution also leads to the following problems. As you saw, complex dependency graph. Services depend on each other, and as the graph of those services grows, dependencies become more complex. Custom contracts between services. Service owners engage in custom contracts, such as notifying each other when something happens. For example, Service A may notify Service B when something happens, but it may also engage with Service C about something else. So now Service A owns a lot of custom contracts. Delivery warranties. So what happens if one of the downstream services is down? So Service A has to notify Service B, but Service B is down. Then Service A is forced to engage in some kind of practice to handle this case. And performance. So performance can be an issue because as all these requests go back and forth between services, services might be impacted. A bad actor can put a lot of pressure on the whole system, and high throughput services can also be impacted by underperforming services. It also leads to the following questions and situations. How to handle downtime. This is especially hard when services are somehow tangled and coupled. Rolling out changes. This requires a high level of coordination, involving an API or applying security rules, for example. Deprecating a service. This tends to be very disruptive and leads to migration in multiple services. Understanding the state of the system. How do we get metrics about what's happening in the whole ecosystem? And insight. Who depends on who, and how is everything flowing in the whole architecture? So let's talk about events. So what's an event? An event is a change of state, an occurrence, an incident, a circumstance, anything, anywhere. This means that events can represent anything we want and that they can come from anywhere. Any service can actually emit events. So we are surrounded by events. Events can be as important and meaningful as we want them to be. The importance level comes from what the event represents in the domain area we're working on. This is what defines if we care or not about a particular event. For example, if I'm working on database infrastructure, I may care about every time a connection is created, closed, a transaction succeeds or fails. On the other hand, I may or may not care about a particular value of a column being updated on a particular table. So let's talk about event-driven architecture. What is it? It's a paradigm, meaning that it's a pattern or a way of writing software. That it's based on event operations such as production, detection, consumption, and reaction. And it promotes loosely coupled and distributed components and services that are horizontally scalable, highly available, and resilient to failures. So from a very high level, an event-driven architecture consists of an emitter or an agent that is responsible for detecting, producing, and transmitting events. A channel, in some systems, is also called a topic, which is the medium how events get propagated in the form of messages. On simple architectures, channels tends to be a queue, while on streaming or real-time applications, channels tend to be active sockets or some kind of subscription. The last component of this architecture will be the consumer, also called a sink in some systems. The consumer is in charge of processing and reacting to events. So one of the main characteristics of this architecture is that the emitter doesn't know anything about consumer. In fact, the emitter doesn't even care if messages are being filtered or consumed. This is a key principle to keep services loosely coupled. Events get announced without caring about the consequences, meaning that there is little to none space and time coordination or synchronization. So based on what I just mentioned, let's revisit the original example that I spoke at the beginning. We can see all the direct coupling and connections in the original design. Now, let's take a look at the same example, but implemented with the event-driven architecture. So let's focus on what happens when we add a movie title. In this case, once the title is added, the movie registry service is no longer going to be communicating with any service. Instead, the movie registry service is just going to produce an event and transmit it via the channel. Then, other services will subscribe to this channel and consume the events that indicate that a new movie has been added. This is a very simple example, given that our movie registry service is not a high throughput use case. But think about use cases such as telemetry or logs, where you may want to be able to react when something changes. The same idea can be applied to all services. Each service can produce events for anything that happens without really worrying about which service cares, the state of these services, or how are these events being consumed. So as you can see, this architecture breaks direct coupling between services, which removes the complexity at large scale. So how are events represented? So events are represented as messages, and they usually have a schema. The schema usually contains a version, which is very useful to understand how the event message may change over time. An ID, a unique identifier, very important for traceability and debugging purposes. Timestamp of the event. This is useful for consumers, especially to understand the state of the system, to understand when this state change actually happened. The type, for example, a movie title has been added, a movie metadata has been updated. Those can be types, and this is useful from the filtering perspective. A stream of events is like a water hose. Without any filtering options, it might be overwhelming and even useless. It might be too many events coming in, and you're not going to be able, like some system might not be able to process this so fast. Payload, any information about the event itself. For example, the movie ID. And metadata, the source of the message, where the event comes from, like IP of the host who announced the event, or the name of the application, and so on. Message timestamp, and this is very important. This is very different to the event timestamp. They usually tend to be the same or very close. But the event timestamp represents when the state change actually occurred. The message timestamp represents when the message was actually emitted. So there might be some delay in this announcement, and that's why it's good to have these two, because it actually communicates downstream services if there has been some delay, or at least a common delay between when something happens and when it gets announced. So let's keep event messages lean. This is very important, and I cannot emphasize this more. It is very easy to fall into the trap of wanting to add as much information as we can into the message. However, this leads to problems such as exceeding the maximum payload size. So depending on what technology you're using for transmitting the message, the event as a message, you may have a maximum payload size. And since all these messages are technically machine generated, it's very easy to exceed this payload size if we're not careful. Also, our producers may run out of memory by serializing the messages before they put it on the channel. Same thing happens with consumers. Consumers may run out of memory while reading the message and deserializing it. And then you also may deal with situations such as messages containing stale information. Say that a message might be associated with some kind of counter. Including the value of the counter might not be ideal because it may lead to stale information by the time the message is consumed. Instead, messages may contain a reference or an ID that can be used by the consumer to fetch the counter from the original source. So the event-driven architecture has the following considerations. Responsibilities. It is important to understand that event-driven architecture puts a lot of responsibilities on consumers. Therefore, if you're driving the adoption of this architecture, you may want to provide a framework, a platform, or a client for people to ease the transition into this pattern. Message contracts. It's very important to communicate how events look like. What's the schema? Are the events version? Warranties. It's highly important to clarify if messages are going to be treated, how announcements are going to be treated. For example, we are going to announce at least once, meaning that we may announce once or twice, only once, which is a lot of the time is the expectation. Best effort, meaning that we'll try to announce, but if we can't announce because we have some communication issues, then we forget about that event. So it's critical for consumers to understand this before they can build on top of your platform. This also leads to idempotency. It's very important to clarify if the expectation of processing the same message multiple times will lead to the same result. For example, the counter use case, the counter example. If you include the reference to the counter and then the consumer has to go and fetch the counter, is the expectation that once you fetch it the first time, you're going to get a value, and then when you fetch it the next time, and the value is going to be the same or is it going to be different? This is important to clarify. Message ordering. Are events going to come in the order as they are created? Is that something that consumers can rely on? Message delays. So when dealing with event-driven architectures, you may find that you're going to have certain issues communicating with the channels. And it's important to define how you're going to handle delays. So if the service is having issues communicating with the channel for some time, what is going to happen with the events that you're trying to announce? Does it make sense to announce delayed events? What's the impact for the business if the events are delayed? Logging and insights. Extremely important to have logs indexed in a way that they can be used to understand what's happening in the system, what events have been announced, for example. Metrics. It's part of understanding the whole system. Archival and retention. Being able to archive events for some period of time is highly important when it comes to auditing and debugging purposes. For example, people may want to understand what happened in the past 10 days, and looking at all the events might be the answer for that. Reproducibility. So are we able to replay or re-announce all the events in a time range? This is especially important if for some reason we either miss events, we ignore some of them, or we skip some events due to some issues. So we need to be able to say, okay, we need to replay the last hour of events for people to consume. Now, let's talk about the event-driven platform, the event-driven data platform at Netflix. So our data platform is composed by multiple services and components. However, part of our goal has always been to make the platform feel like a single entity, because it's easier for users to understand. They deal with the data platform, they don't deal with a lot of different components. We have been able to achieve this by building tools and abstraction layers that provide the right constructs for people to build on top of the platform. And one of the many things that we have built, we created an event-driven platform that we called Microbots. So what is it? Microbots is a unified event platform, special emphasis on platform. I'll go over this in a moment. That it consumes events from multiple services, with the goal of providing users an application an easy way to react to events. Microbots is based on if this then that idea, which means that it's fully aware of events, and it provides templatized triggers or conditions to filter events based on what you care or need, and templatize actions as a way to set up a side effect or a reaction to an event. The goal is to decouple microservices and to have a reactive platform. So we want to be able to react to anything that happens in our data platform. So as I said, Microbots is an event platform. The reason why we call it a platform is because we ingest events from multiple services, and we provide templatized conditions and actions that can be mixed and matched to satisfy use cases. By offering conditions and actions that can be mixed and matched, we're leveraging a tool that allows people to react to events without maintaining infrastructure to consume events in the data platform. So this is a very simple example that we use when we were creating the initial prototype. If table X is updated, then send me an email. So in this phrase, basically, you have if table X, that will be the trigger, then send me an email will be the action. Altogether is what we call a recipe. So we took this idea and we extrapolated it and used it to integrate complex services and drive a wide variety of use cases. For example, if your workflow fails, then send me an email. Or instead of sending me an email, then perform some HTTP request. So Microbots provides a UI for users to create recipes by selecting triggers and actions depending on their use cases. And here's how it works. Microbots may have multiple recipes defined. As events comes in, one event may activate multiple recipes. For each recipe, the event is evaluated against the trigger. Triggers that satisfy the condition will lead to action. So for example, say that I get an event indicating that table X has been updated. In this case, all the recipes where the trigger looks for table updates are going to be activated. Next, Microbots will evaluate each of these triggers and see which of them cares about this particular update, meaning which of them actually cares about an update for table X. Those that actually care about table X will be the ones that are going to be considered positive. The other ones will be considered negative. Only the ones that are positive will execute the chosen action. So if we look at this graph, the event comes in, it activates all these recipes from trigger 1, 2, and trigger N. Trigger 1 and 2 that are like highlighted in this graph are the ones that are actually evaluated, that the evaluation results as positive. Trigger N did not. So the action that is associated with the trigger N will not be executed, while action 1 and action 2 that are associated with the positive triggers are going to be executed. So we build Microbots by convincing multiple service owners, initially in the data platform ecosystem, to start emitting events about what's happening in their services. The main idea was to be able to react to anything that happens in the data platform and to execute actions that could drive other use cases. This means that instead of relying on a time-based trigger or pooling mechanisms, we introduced a new way to execute work when it was actually needed. So a good example of this will be to execute a daily report about some metrics. We may want to execute this report at midnight because we assume that metrics are going to be ready around that time. But what happens if metrics are delayed? Then I may decide to execute the report at 2 a.m. just to give me some buffer to wait for metrics. But what happens if metrics are there at 8 p.m. and I'm just waiting for no reason? Or even worse, if metrics are never there, then I will be executing the report without having metrics being ready to consume, or no metrics actually. So Microbots solves this problem by allowing you to say, if metrics are ready, then execute the report. There's no time involved. There is no pooling mechanism involved. At a high level, this graph outlines all the services producing and transmitting events over channels and how Microbots subscribe to them and to react to these events. So A quick summary of this graph would be like MetaCat is our metadata warehouse. We have the scheduler, which is our workflow orchestrator, Genie, which is our job orchestrator, and we even consume events from AWS S3. So all of these are emitting events, places them on channels, and microbots basically subscribe to these channels. And then all people can come create recipes to react to these events. And part of the actions that we provide are some of these. For example, you can hit an HTTP endpoint with whatever payload you want. You can go and update some metadata or metacat. You can trigger a workflow in the scheduler, in the workflow orchestrator or the scheduler. You can send an email. You can route some of these events to Kafka. So if you have a Kafka topic, you can send it there. It's in our case, Kafka is Keystone, which is our Kafka platform. Or you can actually send it to Atlas, which is our time series metrics tool that allows you to set up dashboard for metrics. So you can say, I will want to count how many times a table has been updated per minute, per second, per hour, something like that. And you can set up dashboards in a matter of minutes. So in terms of use cases, Microbot is able to aggregate events and react to them. So instead of saying if table X is updated, I can actually say something that if table A and table B and table C are updated. So you're talking about different events, and Microbot is able to aggregate them and then react to this. Trigger workflows or release jobs. So we integrate with the scheduler or the workflow orchestrator, and we're able to say, well, when something happens, then let's execute this workflow. Or our jobs may say, well, I have some dependency on a table and I don't want to execute until this table has been updated, for example. So the job is in a waiting state, and then Microbot is able to release this job. It drives integrations outside of the data platform. So now that we are collecting events from inside the data platform, it's very easy for people to come and say, well, when something happens in the data platform, I may want to execute a script or may want to hit an HTTP endpoint or something like that. It reacts to S3 objects. So for example, a use case we have is that we want to emit events, we want to execute or emit reports when some S3's object shows up. And we're able to do this because we listen to objects that show up on S3 on a given bucket or a given path. It's able to react to workflow failures. So for example, if your workflow or your job fails, we are able to say, well, let's execute this script that is going to gather some information about the failure and then notify the user. But if you think about it along the same lines, we can also say something like, let's execute this script to try to remediate the failure and re-trigger the workflow. It allows you to set up conditions to do metrics. So for example, you can count the number of events of a certain type, number of workflow failures grouped by owners. You can even slice it using the filters that we provide. And it provides insights. Since Microbot is exposed to a large variety of events, it allows you to search over the events that come in, see what conditions were applied, and which of them were satisfied and what actions were taken. So in addition to all the use cases, Microbot is also becoming the source of truth of what's happening in the data platform. Since Microbot archives all these events for a period of time, you can imagine people asking us questions such as, can you tell me how many times a table has been touched in a particular hour? By looking at the events, this is a relatively simple question to answer. And this is part of the functionality that Microbot also makes available via search interface in the UI. So in terms of scale, Microbot processes around 30 million events a day. It evaluates around 300 million recipes a day. And it executes around 40 million actions a day. So you can see the scale and the size of the problem that we're handling with Microbots. Microbots is a high throughput use case. And all of this has been written with Python. In terms of lessons learned, Microbots is a critical service. So Microbots became a critical service given the amount of events that are being followed into it and the services that depend on it for event propagation, reaction, and consumption. So if microbots is down, event messages simply just sit on the channels waiting to be consumed, which means that no action is taken. So microbots owns a big responsibility at this point. But with that responsibility, it also was able to solve the problem of coordinating deployments between applications. The need for specialized levers or maybe strategies. We need different mechanisms to deal with bad actors, such as services floating only with events or downstream services underperforming. So think of a broken endpoint, for example, or a service is struggling with the load. We need levers to decide to control how much we can process for a particular service. Event lineage, excuse me. Event lineage is highly complex. Understanding, excuse me. Okay. Understanding the life cycle of an event in this kind of platform is very hard because an event can come in, activate multiple recipes, and execute some actions. That's very easy to trace. It's one degree, one level of relationship. But imagine that event comes in, triggers a recipe that executes an action, which action is actually a script. Then whatever that script does is actually very hard to trace back to the original event. To give you a clear example, if table X is updated, I want to execute a script. And if inside that script, I update table B, for example, table B, that update is actually going to create a new update, a new event. It's very likely that event is not going to have any trace associated with the original update to table X. So it's very challenging to be able to build lineage and trace what's happening. Event thinking is hard for users. Every now and then we get questions from users asking us to add support on microbots to either pull or execute on a time schedule, even though we already provide a scheduler in the data platform. So this is what I was talking about at the beginning of the analogy. Metrics are critical. So many times we build software and we set up metrics later during the process. Having a good breakdown of metrics and classification of this is very important to understanding what's happening in a system of this scale. Self-healing, and I say that in quotes. Microbots relies on queues as communicating channels. If microbots is facing some issue, events are either going to go back to their queue or stay there until they can get processed. This is great because we don't lose any events. However, this can lead to a big backlog of events and recipes waiting to be executed. And this also causes downstream issues and long delays. And leverage. So triggers and actions can be mixed and matched to create asynchronous bridges between different services. So also since triggers and actions have a clear definition, adopting new use cases is pretty straightforward for us. So let's go over the advantages of the event-driven architecture. So distributed and scalable. The nature of this architecture allows you to plug in new services without impacting upstream ones. Additionally, it also allows you to plug in more consumer instances to handle the load easily. Fault tolerance. Because of this distributed nature, if one of the nodes or consumer instances is having issues, a new instance can come up and actually take over the work. This is especially true if your workers are stateless. Service independence. By being asynchronous, services are able to adapt without depending on each other. So you can think of one service wanting to scale up to process as fast as the service can, while other services are okay with dealing with some backlog and eventually catch up. And less coordination and flexibility. So downstream services are able to iterate and evolve faster without tightly coordinating with the services and the events. Additionally, the code can be deployed without causing minimal to non impact. So I say minimal because in some cases a deployment may cause some delays, and downstream services might be responsible for remediate themselves or to catch up. In terms of disadvantages or challenges, we have found stale data. So the asynchronous nature of this kind of system opens the door of events containing outdated information by the time they're consumed. Remember that example of the counter that I mentioned a few slides ago. Granularity. Depending on the type of events and use cases, services might be forced to aggregate events in order to react. This is particularly difficult in distributed environments because it requires introducing some state that can be very hard to handle at a large scale. Additionally, in some cases, the number of events, because they may be representing a very small scope, can be very large and lead to a very large volume of messages. Complex consumption strategy. For example, how do we handle duplicate events? Does ordering matter? This could be a problem as consumption happens in a distributed way. Like if you don't have a single instance and the state is distributed, then it could be very hard to handle. Also, how do we handle failures? If we fail processing an event, do we retry? Maybe we just ignore, maybe just archive the event and move on. So these are tricky questions to answer depending on the use case. Archival. Storing all the events in a searchable and auditable way. This might bring some challenges and additional infrastructure. And rate limiting. The processing rate can become problematic depending on the incoming rate. So too many incoming events can lead to a large backlog. Processing too fast may put a lot of pressure on resources such as databases or endpoints and may cause availability issues. So in summary, I would like you to consider the event-driven architecture as an approach to decouple microservices and gain flexibility at large scale. Keep in mind the analogy of the imaginary world with no alarm clocks. When coming up with solutions and evaluating if your approach is being very naive or very simplistic. On the other hand, as you saw during this presentation, this kind of architecture does have a cost and might not be worth it at small scale or for prototyping purposes. That's all I have. Thank you very much.